Next up is a talk by Michael Kubacki. Michael works at Intel, and here you will be talking about how Intel is putting their closed source firmware, parts of the closed source firmware, and opening them up step by step, piece by piece, in what they call a minimum platform. So give it up for Michael.
Thank you. Thank you for attending my presentation. My name is Michael. My co-author was Nate on this. I'm here today to talk about the EDK2 minimum platform and the changes that Intel is making to bring more of our what we call platform code into open source. If you've caught a glimpse of Intel's open firmware strategy recently, you'll see, whether it's from System 76 or from even last year's OSFC keynote by Vincent Zimmer, this min platform topic come up. And so I'm going to explain that in more detail. As part of explaining that, I'm also going to cover some of the background needed. So I understand a lot of people here come from diverse firmware backgrounds, and you might not be familiar with all the terminology. So I'll do a brief build-up into the min platform by covering the background and the pieces necessary to build an open platform with what Intel is providing. So Intel breaks our firmware into three major pieces. This has implications on the way that we deliver firmware and the way that we develop firmware, and likely the way that you interact with our firmware. We do this for very important reasons, because separating the pieces out this way allows us to abstract some of the pieces from another through interfaces. We can better leverage code, and we can also better share code. And so the first piece is what we call the core code. This is the piece that's probably most familiar to people here, because it's our main public visible piece of the code base. It's in the Tiano core project in the EDK2 repository. This is typically open source code. This is code that implements what we call general firmware infrastructure, things like timer services, dispatcher, memory allocation. This is the code that we directly use in Intel products, and you can go find there. So all of our EDK2 based code uses the EDK2 core code. On the silicon side, as a silicon vendor, we distribute our silicon initialization code in the form of the Intel Firmware Support Package, or FSP binary. This is typically closed source code. It's a way for us to distribute proprietary code and make it easier to be able to integrate that into other bootloaders. So for example, Core Boot and U-Boot, EDK can all call into this opaque binary using the interfaces described in the Intel FSP specification. And so as a silicon vendor, we provide the silicon init code in the form of that binary. The platform code are kind of all the other pieces. And so whenever you think about everything that goes into a firmware that is not covered by core or silicon, that generally falls into the platform bucket. The platform bucket is typically closed source. Intel, we build reference platforms for all of our products, and whenever we do that, we build a fully functional firmware. The platform code is part of that, and we share the platform code with a small set of licensees, but this is typically the most elusive part of the code base. So if you're trying to build a piece of code, you need something to use your core code and to call into your silicon binary, and that's what the platform code does. And so the focus of this presentation is going to be taking this platform code that we write at Intel, this kind of missing piece that binds the others, and how we're moving that into open source. So before I get started, I just want to show how we develop code today and why we're able to share the code that we can share on the core and silicon sides, and why platform's a problem. And so if you look at the core code, our specifications are maintained by the UEFI forum. We have two main specifications, the UEFI spec and the ACPI specification. The UEFI specification describing the interface between the operating system and the firmware, and the ACPI specification describing an interpreted runtime language that can offer some basic hardware abstraction. The platform initialization spec is generally what makes our EDK2 firmware EDK2, and so the platform initialization specs define how to construct firmware. And so you can mix and match various bootloaders with these specifications, right? Some bootloaders will implement UEFI, some will do ACPI, and then EDK2 does the platform initialization spec. On the silicon side, we have the Intel firmware specification. the Intel Firmware Support Package specification. And this allows us to distribute our silicon code in a way that you can call into the silicon and APIs and be able to reliably initialize the silicon. The parameters, or what we call the UPDs, of how to configure what the FSP does changes, and that's part of the integration guide that we ship. But in general, we try to simplify the interface to do silicon initialization through this FSP spec. And then on the hardware side, we write tons of firmware that works generation over generation. It works with multiple hardware vendors because of the hardware specifications. And so whenever we look at all of this, we see quite a bit of consistency across the way that we develop these pieces of the firmware. But we don't really have anything on the platform side. And so the platform side is kind of left in the wild in terms of what people do to bring all these other pieces together. So getting down more specifically to what the platform does, it defines the firmware flash map. And so you can imagine that's very platform specific or board specific, depending on what kind of security boot technology you're using, or your cache properties. You may choose to adjust your firmware flash map. It specifies the hardware drivers needed and the core drivers needed. So part of having all these other drivers available in silicon and in the core is being able to integrate them into a firmware that's actually used on a particular motherboard. The platform code chooses which drivers to use. It calls into the silicon API, so it will call into the FSP to do the FSP T, ELM, and S APIs for temporary RAM, your memory init, and your silicon initialization. And a lot of the board-specific information, like your GPIOs, serial presence detect, those things are in this code. So if you have soldered down memory, you might have your SPD table hard-coded in your board code. Otherwise, you might read it over SMBus, right? Those details all fall into your motherboard design and into what we call this platform code. So I just want to quickly show where we're at today in terms of the lineage of Intel firmware is kind of a natural extension of the way that we've moved from legacy BIOS into UEFI. And so if we go back to legacy BIOS, which was 16-bit real mode code written in assembly, we realized that as computing systems became more complex, that wouldn't scale. So we needed to move to C code. We needed to have a more robust interface. And so UEFI enters the picture. In 2004, we start to implement the EFI, or the original EDK code, and this code that is compliant to the UEFI specification. At Intel, we start to move to a converged core. So we start to align the product lines around that code a few years later. We move all the segments, so from Atom to Xeon, onto this UEFI code base by 2015. And so at this point, if you think about that core pillar, we're now getting everything on the core code. Then we realized, and it's actually around 2012 this actually happened, but that we started working on the FSP. And so we weren't providing the platform code, and people wanted to be able to wrap their silicon init code. And so projects like Core Boot, U-Boot, to be able to do that in a consistent way, we developed the Intel FSP, and that comes in the picture to satisfy that silicon pillar. And so now what we're left with naturally is the platform piece. And so I'm just showing you now how we go from legacy BIOS to where we are today and what we're trying to do to standardize the way that we deliver firmware so you can use it in a reliable way. From a UEFI platform initialization perspective, we deliver if you look at the hardware on the bottom, the UEFI spec is the interface between the OS and the hardware. We deliver the silicon code in terms of the FSP binary, and then you have all these platform drivers. We have what we call the green H, which is kind of this, it's the PEI, what we call the PEI and Dixie Foundation. It's this set of reliable interfaces that you can use to initialize your firmware that our silicon and our platform code use so that they can be swapped out more easily, basically. It's a stable set of interfaces. So the UEFI PI spec defines the PEI and the Dixie phases. And so if you've worked in EDK code, you've heard of those. And that's what we use in the minimum platform. So if you look at the minimum platform compared to a lot of other bootloader solutions, it complies with the UEFI PI specifications, whereas many today do not. So silicon initialization is a big piece of bringing up your open platform. We do that, like I said, with the Intel FSP. So this is just covering the silicon init side of bringing up a platform. And so Intel delivers the FSP with two primary objectives. One is to distribute binaries of our proprietary silicon code to the public. The second one is to enable this to plug into arbitrary designs. We also realized that initializing the silicon is a relatively complex undertaking. And so a kind of a secondary goal of this is to abstract the complexity of silicon. Many small vendors and other people that don't have the resources to necessarily write all the silicon code generation over generation can rely on using the FSP with its APIs to initialize their platform. And what you're most familiar with today is probably what we call FSP 2.0. FSP 2.0, the main goal of this was to make a binary interface that could be plugged into arbitrary bootloaders and allow you to be able to call into it using a reliable set of APIs. You pass the data in with what we call UPDs, or updatable product data, and you get the results back with handoff blocks, or hobs. This provided the 32-bit entry point APIs, and the FSP spec talks about how to discover and call into those APIs. Underneath, this is really just EDK2 firmware. And so at Intel, we write all of this code using the platform initialization specifications, the UEFI PI specs. And underneath that binary, you'll find that it's just UEFI PI firmware. In fact, we boot this code without using the FSP APIs at all. We just run a straight EDK2 BIOS or firmware, and then we just launch all of this code using the UEFI PI dispatch algorithms, because it's all in firmware volumes, it's all in EFI modules, it gets dispatched and runs. And so what we realized was that this is very, very kind of awkward if you're doing an EDK2 wrapper, because you're basically you're treating this blob like it's not EDK2 code, even though it is. And so there's a lot of overhead associated with that. This is where we introduced Intel FSP 2.1 recently. And the primary objective here is to seamlessly integrate with UEFI PI firmware. This provides two modes, the API mode and the dispatch mode. The API mode operates just like before, but the dispatch mode has an important advantage in that the FSP is treated like a native UEFI PI binary. So that means you don't have to convert from the data structures that are native to EDK2 into the UPDs, and then inside convert back and do this conversion process. You're not converting data structures back and forth as if this is not EDK2 code. So this, in the dispatch mode, we share the PEI core. And so if you're familiar with EDK2, there's a core called the PEI core. And whenever you're using API mode with an EDK2 wrapper, you actually have two PEI cores. And so this leads to a lot of overhead in terms of maintaining the two cores and keeping them synchronized, in addition to the data structure conversion. And so with dispatch mode, we get rid of the two PEI cores, we get rid of the stack switch, we get rid of the two separate PCD databases, the PPI databases, and we start to treat it like a UEFI PI binary, and you get quite a bit of efficiency improvement for that. Once we did all this, though, the problem is we can demonstrate this FSP dispatch mode, but we don't have an open source platform wrapper to be able to exercise it. And so at this point, we realized that it would make sense for us to release the platform code, be able to use this dispatch mode, and demonstrate how you use the dispatch mode, in addition to the API mode already used by other bootloaders. The main thing whenever we looked at the platform code was a lack of consistency. And so the code was written for specific platforms, which means a lot of developers wrote the code so that you just do what you need to do to get the platform up and running. You can touch 5 pieces of hardware in the same file, and there's no real reason why you need to touch those in the same file, other than you just know that you have a rough order that you want the execution to happen in and to initialize the hardware that way. This made writing code to bring up platforms relatively quick for developers, but it also doesn't really lend well to the reuse and the leverage that we want to have in the open source community whenever we start publishing code out. In addition, the code is difficult to understand and debug in general because you have this deviation in implementations. If you understand the way that one implementation is done, it doesn't necessarily translate super well to the others. And doing the same thing different ways always makes things difficult to secure. So if we're writing the same feature in 5 different platforms and you're not sharing code between those, and it makes it difficult to secure and update that code. And so this is one of the areas of improvement that we're bringing, in addition to moving the code to open source, is to move to this minimum platform, this single converged platform code, and then move that into the open and have our platforms be able to leverage from that open source platform core. And that will happen across our server, client, and ultra mobile line. So across from Atom up until Xeon, we'll use them in platform. So if you look at what it takes to go from where we are today to where we want to go, it's quite an undertaking. In GitHub, we have the EDK2 repository and the EDK2 platforms repository. And this is showing the closed source code at the bottom. This is the stuff internal to Intel. And then what we have today in open source. So today we have the EDK2 repository, and it has a lot of packages there. You'll find a lot of MDE module package, and UEFI CPU are some of the more common ones. But there's a lot there. And EDK2 platforms we haven't really used super well, but what we plan to do and what we are doing at the moment is moving all of our platform support code to EDK2 platforms. And so today we have the min platform package up there. And so whenever we started going through all this work, we realized we needed to write a specification to basically describe how to write consistent platform interfaces. So if we're building an Atom product, a Core product, or a Xeon product, there's basically a blueprint as to how you put together the firmware in a way that all the pieces plug together the same. And that specification became the EDK2 minimum platform specification. So we contributed that to the Tiano Core project. And the min platform package kind of has these generic flows about how to do the platform code. So for example, if you need to do board detection or you need to do GPIO initialization, the min platform package defines a linear flow throughout the boot of when that's done. And so if you work on an Atom system or a server system, you can take your knowledge about how the boot flow works, and it's fairly consistent across the product lines. So that min platform package is kind of the core piece. It's open for extension, not modification. We do not change it in order to boot any type of system. We use it as is. Along with that, we have the advanced feature package and the open board packages. And so the idea here is that the min platform package contains this generic control flow that kind of goes through the boot, and it says what needs to be done when. And it's doing the minimum amount of callouts that it needs to do to get the system to an operating system, a UEFI compliant operating system. On top of that, we put all the other functionality into what we call advanced features. And so that moves into advanced feature packages. And so here it says advanced feature package, and we do have that. But what we're starting to move, we're trending more toward, is having separate packages. So we have one called debug feature package, one called power management feature package. And we're kind of taking these high-level classifications of code and moving them into these packages. The main idea here is to keep some cohesiveness inside the package, but also not get it too bloated. A lot of times people look at their files and they see, oh, this package is doing power management, it's doing security, it's doing all this stuff. I don't need all of that. So we're breaking it out in the separate packages. The other interesting thing is we're supplying what we call the board code for every Intel reference board. So whenever we release a product, we'll supply the open board package for a reference Intel platform for that product. The idea here is that you can take this package and you can use it to bring up your own board. So you look at our SPD settings, you look at our GPIO values, and you have obvious places that you can swap out your board information to be able to take that package and bring it up on your board. Today we have the Kaby Lake and the Whiskey Lake open board packages. We plan to add Comet Lake soon, and in addition Ice Lake. And once we're still in the catch-up phase of all of this. Once we get caught up with releasing these, then you should expect it at product launch. So whenever the product launches, you'll get an FSP binary, you'll get an open board package for an Intel reference platform that uses that FSP binary, and you can start using the min platform spec to understand the open board package and how it's interacting with the min platform package and how you can make your board be supported on top of that. The other thing we're going to do is move the features one by one into the open source. So at Intel, a typical platform can have over 3 million lines of code. They're very big. So moving everything into open source is not the greatest strategy for sustainability. So we're going to move each feature now that we've kind of carved out these advanced features, we're going to move them one at a time into the open. And so today we have, like I said, some debug features there. We have some Thunderbolt code, but we're going to move them one at a time into the open and directly use them back into the closed source. And so at this point, our next generation board package, which we work on at Intel up to product launch, will be directly using the Min platform package from open source. It'll be directly using the advanced features from open source. And so whenever you see those packages in open source, although you don't have the next generation code yet, the next generation code will be using those advanced features and will be using that Min platform package. And then once we hit product launch, we move that next gen board package into the EDK2 platforms repo and we continue. So if you look at the open platform firmware stack, the way that we see it is EDK2 is our core code across all of the different computing segments. The Min platform package is there as well. And so whether you're building a server system, client, once again, or a mobile system, those are the consistent pieces that you use as is. The Intel FSP is our way to initialize the Intel silicon. And so once again, regardless of which segment you're working in, the interfaces and the view should look very similar to you as you work across the various products. And then you have these board packages. And the board packages are probably the only piece that you really need to touch. So you take our open board package, our sample board package that we're providing you, and you just swap out what you need for your board, and you should be able to get up and running. Now, whenever we start talking about minimum, a lot of people have different ways to define minimum. It seems somewhat subjective on what minimum is. And so in order to talk about the minimum platform and what we mean whenever I say the basic support needed to get to a UEFI compliant operating system, we defined what we call the stage platform approach. And so the idea here is to be able to classify what is needed in order to meet specific milestones throughout the boot. And so if you're going through stage 1, we call minimum debug. And this is the code that you need to basically just get debug up and running on the system. And so whenever we ask, does something go into stage 1? If it's not needed to get debug up, the answer is no. Then we go to stage 2, memory functional, same thing. And so as we start to talk about what to put into the Min platform package, the answer is fairly simple. If it's not needed in order to get through any of these basic stages, the minimum platform stage 1 through 5, it's not going into the Min platform package. And it also won't be executed outside of that stage. So for example, if you're doing a stage 3 boot, which is boot to UEFI shell, you don't need to do ACPI table initialization for that. And so this is the way, the idea behind this is to keep our execution paths clean. And so the minimum platform specification is where we describe the stage boots and why we do them. But the main thing to take away here is that if you want to just do a stage 2 boot and have minimal stuff in your way to get to memory in it and then jump into some other environment, normally we would jump into what we call Dixie IPL, the next stage of our boot. You could jump somewhere else. If you want to just boot to OS and not have any of the other stuff in your way, you just do a stage 4 boot. It takes all the advanced features out. And so we're trying to provide a clean foundation that you can modularly build on top of to be able to construct firmware. And one of the things that we see, and in addition to the kind of classic reasons for moving code into open source, with the emergence of cloud, we think that with the vertically integrated solutions that you see and the smaller development teams that are building firmware for the semi-custom designs that have off-the-shelf processors paired with accelerators, and we think that for those vertically integrated solutions, these open source building blocks that we're providing and the source of advanced features can help. And so what we're trying to do is make this code available that's closed source today, and then you can use it to build on your Intel platform however you like. So this is going back to that original picture and just showing that the silicon code becomes Intel FSP in this. Your platform piece becomes Min platform. On top of that, you have your board code and any other drivers that you may need, such as the Intel GOP driver for graphics initialization, things like that. The basic point of this is that the UEFI was built with the PC supply chain in mind. And so there is a great deal of flexibility in terms of the PCI spec and how you mix and match components from various vendors. So binary compatibility is an important piece of the specification. And so we're continuing to support that model because realistically, that is the way that the large-scale OEM PC ecosystem is operating. But at the same time, we're opening up as much code as we can to be able to be plugged into these smaller designs and people to be able to experiment and innovate on the Intel hardware. So what can you do? This is some of the things that we look at as people getting involved is you can create and modify Intel system firmware. So we encourage you to go take the open board package for one of our reference platforms and port it for your board. We encourage you to share platform features and use our features. So if you could enhance our features, or if you want to contribute features or get involved there, that's also a way to do it. Embedded system development is another place that we see. So the simpler execution paths, we hear a lot of people say, whether they're doing emulation or simulation or a simple embedded device, that they just want a simple way to get memory initialized and then jump into their embedded operating system or do some IP checkout. So inside with like some EFI app or something. So there's a lot of environments we think that the simpler execution flows with the advanced features moved out of the way can help. And if you want to create a new board package, this is kind of the overview. So I'm just going to show here. It's not super complicated. You start with our sample open board. You update the board specific information. You can get you can boot through the stages. So we encourage you to do a stage 1 boot, get your debug working. Do a stage 2 boot, get to memory in it, and bring it up one stage at a time. And then in addition to that, you need to configure the FSP for your specific board. And so you can use your FSP integration guide to do that. This is the current status of where we're at in upcoming plans. So we currently support the Kaby Lake platform. We have the Kaby Lake U DDR3 RVP. In addition, as System 76 said, we have partnered with them on bringing this to a commercial system. We understand that not everyone has access to Intel reference platforms, so we're bringing it to the Galago commercial system. That one we actually have booting to the operating system now, so that's been an ongoing effort to try to do that. As part of this commercial work, I would also note at Intel, we typically have quite a bit of debug capability on our platforms. One of the things that we found whenever we went to the commercial one and we started actually trying to do this ourselves, take our open board and move it to a commercial system, there were quite a few challenges that we're trying to address and make easier for people. One of those is closed chassis debug. And so an example here is we're putting out a new driver that can actually do BIOS debug messages over the HDMI port. And so you can use the I2C lines that are normally used for EDID, and we can send BIOS debug messages over those to a bus pirate that's operating in slave mode. And so we've also done things like move a lot of the build tools that we use to Linux and test them as well on various Linux distributions. And so we're trying to make this all more friendly and easier to use across the environments. But that documentation, it's not in the upcoming plans. That's something that we do plan to expand on as well. So we understand that Core Boot has good documentation. Intel Slim Bootloader has good documentation. And so with the Min platform, we're also going to put some of those how-to guides and practical information about how do you get the debug over the HDMI port? How do you flash your firmware? That type of information we're going to be publishing. And this is our three main kind of imperatives at this moment is we want to continue to roll out more Intel open source platform code. So as Intel, we realized that we need to kind of unlock this code. So we're primarily focusing on getting the open board packages out. That's one of our primary priorities. And then the other one is expand the advanced feature code and quality. And so as we get these advanced features out, we want to keep modularizing the chunks of our internal platforms and moving them out to advanced features and then pulling them back in to our platforms using the Min platform model. And finally, we want to support open source community continuous integration. And so this is one of the places where at Intel, everything that happens on the EDK2 and the EDK2 platforms mailing list, we have CI running inside the company. We're doing GCC 5, Visual Studio 2015 builds. We're doing Xcode and Clang builds, but none of that's publicly visible. And so one of the other things that we want to do in the next few weeks here is move that into the open, so it's publicly available. And with that, that's the end of my presentation. So I'm happy to take questions now from anyone.
Thank you, Michael. Give a round of applause, please. We have time for about 10 questions. So please step up to the microphones if you have any.
I'm curious, do you know how it impacts the schedule for, say, ODMs to deliver a new board? What's the old time for building a firmware image for a new system versus using main platform?
So we haven't directly worked with any ODMs yet. What we hope will be the case is that we'll start to develop these stable pieces of functionality in the open source that the community will continue to use, and we can improve both from a security and functionality perspective, and that'll make integration into the designs much easier. And so what we're doing is we're basically just moving this out to the open, and we're going to support it and just see how people can find it to improve products. And that's what we're doing from Intel's side.
Hi, I used to be the U-boot x86 maintainer. I'm really impressed with what you're doing here. I just wanted to know, though, is there any interest in open sourcing the FSP itself and that platform in it that Intel has?
Yeah, so the FSP is, if you look at these open board packages, one of the things that we pair with it is what we call a silicon package. And so if you go to the EDK2 platforms repository, you'll find that we have a Kaby Lake silicon package. We have a Coffee Lake silicon package. And so we've started kind of moving some of this silicon init code into the open source and pairing it here. And that's one of the things that we are looking at, is how to bring more of that code into the open. But as far as this minimum platform initiative goes, the main focus right now is getting all this platform code into the open and using the Intel FSP that we release.
I have a question. Is all you're talking about mini platform is a very good concept, but it's still one platform, right? But have you considered a mini platform is actually considered a main platform with device around it? For example, like the notebook at home can actually control everything from your switch, your other device, right? Light bulb, and that. So the platform is actually not a physical platform, but it's a connected platform. So like to address the world that everything is connected.
So you're talking about like a system.
So I want a mini platform is not for boot purpose. Is, for example, it's a CPI component actually can be plugged in another platform. Which
okay. I think you're kind of alluding to the advanced features. And so the advanced features, the idea, maybe I wasn't clear on that. The idea behind the advanced features is that you can plug them into any min platform. And so that's one of the things that we're working toward. We're not quite there yet, but we want to get the advanced features such that whenever you have an advanced feature, if it works on Kaby Lake Open Board, you can use it on Whiskey Lake Open Board. And if you're working on board packages, you can upload those EDK2 platforms as well, and just show how you're using that feature. And so one of the things that does happen whenever you're using these features is if you make an update to one, it affects a lot of people now. And so uploading it to EDK2 platforms is probably, I think, the better way to ensure that you're able to get the support you need if you're using the advanced features. But I think that's a good point. We do have the advanced features able to plug into the various open platforms that we deliver.
Yeah, I have a short question about the platforms that you deliver, because for some platforms, for the Coffee Lake, you have Slim Boot, bootloader support. For others, you have Core Boot. For others, you have the Min platform. Looking forward, what will be the platform, or the primary firmware that will receive most testing, and if you start a new product today, should you base it on Core Boot, Slim Boot, Min platform, U-Boot?
So the way that we look at this, and I look at it, is there's not necessarily a best solution. I think that all of these have their purpose. And so the difference, if you look at kind of the difference between this and Core Boot and Slim Boot, is this is fully UEFI PI spec compliant. That's number one. So you can use FSP dispatch mode. You can't with the other solutions, right? Whether it's Slim Boot or Core Boot. The other one is this is BSD licensed. It's not GPL licensed, and so that helps with some people. And this is, I think it integrates better with the way that the PC supply chain works today. And so if we're talking about people that have commercial systems today built on EDK2 firmware, this is fully EDK2 compliant and kind of satisfies that need. And so I think depending on your licensing and your goals with your system, you could use any of them. What we at Intel are hoping to do is to make building firmware on Intel products easier. And so it's not about using Min platform or using Core Boot or using, it's about what your needs are, having these resources available to you, and then you can make the decision about how you want to build the firmware on there.
Okay, thank you.
Hi. I just wanted to check, when you put this in the EDK2 platforms, are you planning to put a documentation there? For example, normally you have a very good documentation in Tiana Core. So for example, for the Min platform and for the advanced features, you will be having some documentation on guiding how to port it to one's own board?
Yeah, so today we have the minimum platform spec. That's our main documentation at the moment. That's like 100+ page document that explains the architecture. It explains the interfaces between the board code and the platform code and why we're doing what we're doing. That one, everyone's open to contribute to. So that one, you don't just have to take as, the spec says it's this way. That's an open specification. It's in draft state. So you can definitely give feedback, and we would highly encourage you to give feedback on that. The other piece that we have is we have the readme.md in the GitHub repository that has the quick, practical get up and running information. And then the other thing I was kind of getting to in the presentation was we want to get to more of the hands-on documentation, kind of like you would find in the Core Boot and Slim Boot repositories. If you go to their wikis, they have information about how to understand the memory map, how to basically break apart your IFWE and see where the BIOS is. And so we'll be building more of that. That's kind of the missing piece at the moment, but we will be adding that kind of practical hands-on guide soon.
Yeah,
Where is it? We have about time for 3 more questions.
okay. Just one more question about the software label control. Right, if we're working on the open source Linux, we have long time stable label, right? Like Ubuntu 16.064, but in the firmware world, like we see EDK2, we have thousands update, throughout the year, and then maybe we make one label, but nobody really knows, right? When you ship a product, what kind of version of your firmware is. So end up everybody is keep up one version, but from my experience before with the Phoenix, nobody want to update the kernel version.
Yeah, that's a good point. So the EDK2 project has what are called stable tags. And so I believe it's every quarter we do label the code and do a very comprehensive validation on the code and produce that stable tag in the repository. You'll find the stable tags there. Prior to this, we did UDK releases. So we had these things called UDK 2017, 2018. And so we do have a concept of similar to Linux of having these release milestones. And there is validation done at those. Yeah, so I think that's there today for EDK2. The EDK2 platforms, the nice thing that this brings is that this platform code actually uses the tip of EDK2, and that's fairly rare. If you look across the PC ecosystem today, most people are building firmwares that latch on to a specific version of EDK2, and it's often a fairly old version. And so whenever you go get these open board packages, we're actually doing the CI with the tip of EDK2. And so you're getting the code that works with the code you see in the EDK2 repository. And so that's another benefit to moving to this. And we look at that even in terms of deploying security updates and getting patches and fixes out much faster, being able to just have it pushed into the open and people go find it easily is, we think, a nice improvement to have for where we are today.
We have time for 2 more questions.
So I do happen to have two questions, if I'm not using optical. The first is, you said that, so now the FSP, right, can be called through 2 different modes. One is the API mode, another is dispatch mode.
Yeah.
Right. So does that mean, so how do you make sure that in your validation, in your internal validation, you do validate both modes thoroughly?
Okay. Yeah, so that's another good point. So in the validation, this is one of the things that we talked about whenever we move to these FSP modes. We choose the default mode for the particular product, and so we'll do that as every check-in that we do, we validate against one of the modes. And so we choose that mode, and then we move the other mode to like daily testing or a more delayed testing. But whenever we release the FSP binary, both modes, if they're indicated, so whenever you look at the FSP info header, there'll be a bit that'll say whether it supports dispatch mode and supports API mode. If both modes show up as supported, then those modes are validated by the time that binary is released.
Okay. So as an extended question, so when you validate the FSP mode, so you have FSP for different SoCs.
Yes.
Right? So for different SoCs, the FSP binary is different.
Mhm.
So how do you make sure that when you validate the FSP for all different SoCs?
Oh, we have SoC specific validation.
Mhm.
And so every product that we make, we have a very large validation team that does full validation across that product. And so the FSP is part of that. Now, the other thing to mention while we're talking about that is the FSP gets posted on GitHub. So there's the FSP repository. If you go to the master branch there, you'll find all the FSPs for Intel products that have FSP binaries. The open board packages use that binary directly. And so it's not like there's anything hidden or you have to go sign up for. You just go to the FSP repository, get the FSP binary, go to the EDK2 platforms repository, get the open board package. The open board package will already be written to use that FSP, and you can boot it up on your system. And that's the one that we're validating for the open board package. So you can kind of make the link between those.
Another question I have is that in the current UEFI spec and the PS spec, that the FSP code, right, they interact with the code of the rest of the UEFI EDK2 through the PS spec and the UEFI spec, or the DXC protocols and the PI protocols, right?
Yep.
Now you're actually switching from that operation mode to dispatch mode, right, within the main platform concept.
So dispatch mode is fully compliant with all those specifications.
So you don't actually have to modify the spec.
Oh, no. In fact, this embraces the spec. Because now we're not pretending that the FSP is not an EDK2 firmware volume. We're just saying it is a firmware volume. Here you go, dispatcher. Find the EFI modules inside and dispatch them.
Right. So it used to be mangled with others into the firmware volume.
Yeah.
But now it has its own firmware volume. That's all you are.
Well, the TEM and S have generally had their own firmware volumes, but we put the firmware volumes together into an FD, we call it.
Right.
The code has the ability, whenever you use an interface called install firmware volume, it can we give it the address of the element S firmware volume, for example, and it would know how to parse it and move the images that it finds into the list of images for the dispatcher to be able to invoke. And so it's a very natural process. It works the same as if you just wrote, it is native EDK2 code, right? So if you were to write your own code and put it into a firmware volume, it would be dispatched very similar to this. There is, though, if you are planning on using dispatch mode, do check out the Intel FSP 2.1 spec, because there are special things that you need to consider. So I think that's maybe your point, is there's a little bit more you need to think about. One of those is the PEI core. We only have one PEI core that gets used. That's the one in the FSP binary. It's supposed to be. It doesn't have. There's an alternative boot flow in there that talks about if you don't want to use the one in the FSP binary because you want to use your own with your own stuff compiled in. But if you're using that one, you have to produce a special PPI and go through the process in the spec that is described there. So if you are going to use dispatch mode, just read that section of the specification and use your FSP integration guide, and you can get the benefits of the dispatch mode.
Thank you.
Yeah.
And that's about it for questions. Please have another round of applause for Michael.
Thank you.
Thank you, Michael.